Can I? Hello there. I'm going to present this paper from my colleagues from Brazil. I'm not an author. He had a problem with his flight and asked me to do this. Okay. Well, here we have our work, development of machine learning models to predict strip breakage during the aluminum cold rolling process. Here is our agenda with the following topics: background, research problem, methodology, proposed solution, results, and discussion. The rolling process is characterized by gradually reducing the material's thickness until the customer specification is reached. This industrial technique provides final products with specific characteristics such as better surface, finishing, and greater material resistance. In the left picture, we have an example of a basic representation of a rolling mill. On the right, we have an animation and architecture of thickness reduction. In this case, the animation is not working because it's just a PDF. Structurally, hot and cold rolling mills have similar characteristics, but some particularities such as production process, the temperature of the material to be rolled, the surface quality, and the final use of the aluminum. Here we have two distributions about cold and hot rolling process. For cold process, initial thickness are about 5 millimeters and final thickness about 0.0063 millimeters. Working with temperature below 100 Celsius degree, and the final use to packaging for packaging and molds application. For hot process, initial thickness are about 400 and 500 millimeters, and final thickness less than 10 millimeters. Works with temperature higher than 350 Celsius degree, and the final use to stamping applications. Until it reaches its final specification, an aluminum coil can go through several lamination paths depending on the process and manufacturing strategy. A rolling mill may be responsible for one or more paths for the same coil. Below is an example of the distribution of rolling mills in a production line and their respective thickness reduction paths. Here we have an example of distribution for cold rolling aluminum process, and we named the coil mill A, B, and C, and cold mill L1. That is the focus of this research. For example, cold mill A with initial thickness of 5 millimeters reducing to 0.4 millimeters in 3 passes. And the next coil, and the next cold mill B gets the coils with 0.4 millimeters and deliver with 0.085 millimeters. And the L1 cold mill reducing the thickness between 0.085 and 0.015 millimeters. And this reduction of 0.036 to 0.015 millimeters was the past focus of this research. Here we have our research problem. During the cold rolling process, a typical problem frequently occurs. Coil breakage, also known as strip breakage, is one of the main degraders of aluminum cold rolling process. A survey of breakdowns for L1 mill was carried out over a period of 5 years. As you can see on figure 4, strip breakage occurs when the material breaks during the lamination. And the table results surveys show a total of breakage about 1,000 per year. Mean downtime in minutes around 15 minutes for each strip breakage. A total downtime in hours and days. representing the real impact of the problem in the business view. Other important feature of the code rolling process is that it has a wide variety of integrating technologies, such as flatness scanning, instrumenting for measuring thickness variation, as well as advanced speed controls, where a large number of sensors are installed and integrated into historical systems, make this environment rich in data. In the left, we have another animation that will not work here, that have the data source from PLCs, EHMs, and historian systems sent to SQL Server database. And this environment is rich in data, provides a high-dimensional data. However, high-dimensional data risks overfitting, necessitating a balance to extract meaningful insights. The challenge is developing effective ML models to address the course of dimensionality to master the problem for this research. The methodology and experimental flow represents the steps using during this work construction, include choosing the L1 equipment and the lamination pass and collection this data on the SQL server, pre-processing and data modeling. So, the step 3, we cleaning and normalizing data. In step 4.1, we training perform evaluation models without turning hyperparameters and feature selections. And next, the performance evaluation 2 in step 4.2, we training and performance evaluation models with turning hyperparameter and without feature selection. In step 5, we perform evaluation 3 with training and performance evaluation models with turning hyperparameters and feature selection. In step 6, we show the results. During step 2 of the methodology flow, a database is created with statistical values such as mean, standard deviation, minimum and maximum for the variables related to the roll mill L1. Furthermore, basic rolling oil and graining process data are also added to the dataset model. So we have the database description in table 2 on left, and for this classification task we have the summary with all the things that you can see in this slide. I mean, the instance, feature, total features, period, missing data, non-informative features, dataset configuration, coils without breakage, and coils with breakage. Our proposed solution is this. According to the initial analysis, the 3 basic models obtain a better result compared to the others conventional models such as SVM, RNA, RL, and KNN. A comparative study was proposed between the DT, RF, and ET models, evaluating the proposed scenarios for predicting breakages related to the aluminum cold rolling process. In table 3, we can see the better performance for 3 based models, a comparison of decision tree based models. Sorry, just a minute. Okay, I missed something here. Okay, in table 3, we can see the better performance of tree-based model. A comparison of decision tree-based models was used to predict strip breakage during the aluminum cold rolling process. Applying hyperparameter stunning and feature selection techniques, reducing the dimensionality of the problem and maintaining the explainability of the breakage event. Although classical hyperparameters are convenient for many situations, they may not be suitable for all situations, specific datasets and problems. Therefore, turning these hyperparameters is often necessary to optimize the model performance. It's important to carry out experiments and evaluate the performance of the model with different values of parameters to find the ideal configuration. In Table 4, we have the grid search strategy to choose the best hyperparameters for DT, RF, and ET algorithms, and in Table 5, the results of hyperparameter tuning. Feature-based feature selection methods are independent of the learning algorithm and seek to identify the most relevant attributes based on statistical or information criteria. On the other hand, the proper methods use algorithms learning process to evaluate the importance of each attribute, considering the interaction between them. The built-in method combines features of both approaches, integrating feature selection directly into the model training process. In this research, we have a supervised problem, and we use a wrapper method with recursive feature elimination technique to feature selection for this paper. And on the right figure, we have the recursive feature elimination functionality. With a small number of features, we got the best performance for the models. In binary classification problems, the confusion matrix records the number of correct predicted values and incorrect results of the models. In this work, true positives, VP, indicates that the coil passed through the rolling mill and breakage occurred. True negatives, VN, indicate that the coil passed through the rolling mill without breakage. False positives, FP, indicate that the break was detected by the models despite its absence. False negative, FN, indicate that the coil was not broken despite the existence of break. Performance evaluation 1 was carried out with the complete set of data and using classical models parameters. In this evaluation, the best performance model was DT, and with TPR value of 0.805 and AUC of 0.849. Performance evaluation 2 was carried out with the complete set of data using parameters optimized models. In this evaluation, the model that performed best was DT with TPR of 0.841 and AUC of 0.906. Subsequently, performance evaluation 3 presented the results of the models after feature selection with 11, 21, and 31 attributes tested in set with optimal parameters of these models. The model that performed best was DT with 21 attributes with TPR of 0.863 and AUC of 0.926. Results and conclusions. The study analyzed strip breakage predictions using a confusion matrix. During the test, out of 1,338 breakage records, 1,174 were true positives and 164 were false negatives. The model performed well with the gold coil class, identifying 2,196 true negatives out of 2,487 instances, with 290 false positives. Multiple methods of comparison of means were applied, where the null hypothesis was rejected, statistically proving that the models have different results. The models indicates that there is no uniform cause for the event of breaks in the cold rolling process of aluminum, and yes, that the breaks are related to various domains such as rolling melee, oil data rolling, and griding of cylinders. Some finds that we found here are better understanding of the coil breakage problem during cold rolling aluminum, development of approaches using ML in industrial contexts, development of tree-based models using real data from the manufacturing industry and aluminum, development of tree-based models with RFA, the wrapper method of selection attributes. We also have these challenges and limitations. Relevant variables such as related to oil rolling and grinding of cylinders were not available. Hide computational costs during the unexhaustive search of optimal hyperparameters for RF and ET models. Hide computational costs during selection attributes using the wrapper method and RFA technique. The development of the research was carried out in the configuration that you can see on the slide. And as future works, we have evaluate the proposed classification models with the addition of new data regarding rolling oil, cylinder grinding, and coil history. Continue the research, evaluate, and approach based on time series using the variables most relevant already identified. Thank you for all you guys.
Thank you very much for your presentation. We went for Q&A. We have another 2 minutes.
Hello, first of all, thanks for the nice presentation. And I'm working on some similar problem, or like, yeah, I would argue like from the methodology wise on similar problems. And my first question would be, so basically you select the hyperparameters using all features, right? So you first do the hyperparameter tuning and then you do like the feature selection. And my question would be, can you exclude the possibility that it it's mutual exclusive? So basically, for instance, if you have like a different subset of features that other hyperparameters may work better?
Well, I'm not one of the authors of this work. I just presented it for a colleague from Brazil. I will put you in contact with him, and I think you can ask him. It's better than me to answer this. Sorry.
No, it's fine. And then basically the second question goes in the same direction, because one limitation you stated was that the hyperparameter search was quite quite computational expensive. And there I would suggest maybe you can try to use some automated machine learning tool to automatically do the hyperparameter tuning. So that's maybe something you could think of for future work.
I see. Yeah. I'll tell Dan about this, and I'll take note of your email address, then we can.
Yeah, okay, thank you very much.
Thank you for the questions, and sorry that I cannot.
It's fine.
Thank you very much for your question, and as suggested, maybe you can email your question to the author for your clarification or suggestions. Thank you very much, and we need to move to the next presentation. Paper number ID 742. Multi-extraction, feature extraction. Next presentation for 15 minutes and another 5-minute Q&A. Please go ahead.
Okay. Hello everyone, my presentation title is Muffin multi-station feature extraction network for remote sensing classification. The report instruction, the method, experiment and analysis, and the summary will be made in the following aspect. The sense classification of high resolution remote sense images can be applied to urban planning, geological design, monitoring, military society, land use and other fields, and land cover for HRSRS has many detailed sense classification involves utilize the detailed information to determine the semantic labels for sense images. This paper conducts a thorough analysis of the productive performance of the current models, revealing several pertinent issues, number 1, number 2, and number 3 issues. This is the overall structure of our model. Image features are extracted using a two-branch network. Then the MAF model is utilized to extract highly correlated features between the TNT branch and the stream branch. Afterwards, the MFF module is applied to preserve the information maximally from the lower and middle layers. Finally, the joint loss is employed to balance the importance of different features, enhancing the module's convergence speed. Let's move on to the first module we proposed, the mutual attention fusion model. We transformed the structure of features. Then we used the cross attention blocks to fuse the features. As shown in figure, we employed the cross attention fusion module 3 times. Generating shallow, medial, and depth level feature representations simultaneously. The formula are as follows. It consistent of a convolution operation, an inhibit operation, attention, and a multi-layer precision. Considering the complexity of science image and the high dependence of certain science types on low and middle level features, we designed a MFF model. As shown in figure, multiple level features are input into the MFF model, which consists of 2 attention blocks and 2 MLPS. Initially, shallow features are fused with the mid-level features, followed by the fusion of the resoluting features with deep level features. Shallow, middle level, and deep level features are denoted as A1, A2, and A3, respectively. The specific formulas are as follows. Finally, we used joint loss, the significant variation in the scale of science image posed a major change for science classification. In response to this issue, we started a joint loss to facilitate the fusion of local and global features, lambda 1, lambda 2, lambda 3, and lambda 4. Hyperbola trace used to balance the weights of different loss. We utilized various evaluation metrics, including overall accuracy and confusion metrics to assess it and compare our approach with existing methods. In this study, the effectiveness of the proposed methodology is validated using the public available datasets UCM, EID, and NWPU. The table shows the comparison of our method with 7 other state-of-the-art methods. The figure shows the confusion matrix on both datasets. we conducted ablation experiments on the AID 0.5 and NWPU 0.2 datasets to evaluate the effectiveness of the proposed method. The following 4 groups we constructed. This approach utilized the MAF module to integrate local and global features, significantly enhancing the impressive power of features. Feature worker can explore techniques such as knowledge distillation and multi-stage training to enhance module performance and training efficiency. Okay, thank you.
Thank you for your presentation. We open the floor for question and answer, if there are any. Okay, one question from my end. What are the improvement could be added in this project or this research?
Sorry, I'm reporting in place of the original author. The original author have some reason correct.
Okay, no issues. Thank you very much for your presentation.
Okay, thank you.
We move next to the last presenter ID number 993. Presenter number 993. Okay, since the presenter is not here, we are closing this session. Thank you very much for your attending.